Previously, we talked about the applications of the integration on how to find the areas between the t curves, right? So let's say we're given t curves, f of x and g of x, right? What does it mean, the curve? So how to find the graph of the curves, for example, f of x or g of x. So by finding a lot of points on there, right? And how to find the coordinates of the points? By taking a lot of axes here, right? And by putting the axes to the functions of the f of x, for example, right? We can find the x and y coordinates of each of the points, right? Do you understand what does it mean? So if I say, hey, let's say we're given the function f of x is equal to the x squared, right? How to do this function? So by finding a lot of points on this curve, right? So for example, you choose a lot of x's. So you choose x and you find the y. So if the x is equal to the 0, what is the y? Is 0, right? You just need to put the x here, right? So this will be the first point, for example, one of the points on this graph. If the x is equal to the 1, what is the y? 1. If the x is equal to the 1 over 2, y is 1 over 4, right? If the x is equal to the 1 over 4, this is 1 over 16, right? So by finding all the points, or a lot of points, and by connecting them, we can find a graph of the functions, right? So do you understand this? So whenever you choose some of the x's, if you put this x to the function, it gives you the coordinate of this point, okay? And if you draw the point, x coordinate of this point tells you the distance from this line, from the line x is equal to the 0, right, from the y-axis. And the y coordinate of this point tells you the distance from this line, from the x-axis. Yes? So here, what I wanted to do is, so if I would like to find the width of this rectangle, one of the rectangles, if I would like to find the width of this rectangle, I need to find the coordinates of the 2 points there. Yes? So if I fix the x, can I find the coordinates of this point? By doing the same way as here, right? I need to put the value of the x to the function f of x. It gives me the y coordinate of that point and above. And if I substitute the x to the g of x, it gives me the coordinate of the point, which is in below, right? So in both of the cases, the y coordinates of the points tells me the distance from the x line, right? X-axis. Y is equal to the 0 line. So if I subtract them, it gives me the distance between these 2 points, okay? Which is the same as the height of this rectangle, okay? So if I would like to find the area of this rectangle, I need to multiply the difference on the y coordinates of these 2 points to the delta x, okay? So how to define this delta x? So depending on number of the partitions, right? So if I'm finding the area between the 2 points on the x between a and b, then I need to make, and if I need to make the n partitions, then the delta x will be equal to b minus a divided to the n, right? Fixed. So if I decide to choose n different rectangles, then the width of each of them will be b minus a divided to the n, okay? Then the idea was like this. So if I get a lot of rectangles like this, so by multiplying f of xi to the g of xi, and I need to sum this from 1 to the n, and if I sum this, it roughly gives me the area between these 2 curves, right? Roughly it gives me the area between the 2 curves. What I need to do in order to get this like an area more precisely, I need to increase the number of the partitions, right? So if I increase the n until infinity, so I will take a lot of rectangles, then this summation, I goes from 1 to the n, delta x, f of xi minus g of xi, becomes the integration of the f of x minus g of x multiplied to the dx from a to the b, okay? So dx here means that I'm integrating this function with respect to the x, and the t boulders, the numbers on the boulders a and b, means how the x is changing, right? I'm changing the x, the values of the x, from a to the b, okay? This is what does it mean here. So do you remember, so we defined the derivatives by the definition using the limits, right? But actually, we never use this in practice, right? So we've considered so many applications of the derivatives, and we never use these limits, right? So we need these limits in really specific cases where the function is like a really specific. Then I need this derivative, the definition of the derivatives, in order to find the derivatives. For example, in your homework in the problem number 6, you need this definition in order to find the derivative. Okay? But for most of the cases in practice, we don't need this definition. But for the integration, this definition is like really important. Okay? So you need to really try to understand the concept of this definition, because like in the applications, many things can be simplified using the integration, and you need to understand how to derive these integrals. Okay? For example, we will consider today the examples of finding the volumes using the integrations. So before we start, let us review. Do you remember how to find the volume, for example, of the cube? Do you remember what was the volume of the cube? Area of the base multiplied to the height, right? So if you're given side here, x, x, and x, right? Basically, in the cube, all the edges are the same, right? So x squared, this is the area of the base, right? Multiplied to the x gives you the volume of the cube, right? Or simply x cubed. So if I say that, hey, this is not a cube, this is parallelepiped, then this x becomes the h, right? Do you remember what was a parallelepiped? So these three sides, there are three sides that are different. For example, the base might be a rectangle, and the height is not necessarily be one of the sides as the rectangle. So we call the parallelepiped as kind of cube where all the sides might be different. Okay, for example, this side is equal to the A, this side is equal to the B, this side is equal to the H. Okay? So do you understand what is the difference between the cube? Right? In the cube, of all of the sides are the same. The height is the same, the sides of the base are the same. In the parallelepiped, there might be different. Okay? What is the volume of the parallelepiped? The idea is the same. A multiplied to the B gives me the area of the base, right? Then I have to multiply this to the H. Okay? A multiplied to the B multiplied to the H. The same idea. You find the area of the base and multiply this to the H. Okay? So the volume in this case will be A multiplied to the B, which is the area of the base. Okay? And multiply this to the H. Here is the same. So this is the area of the base. So if I consider the cylinder, do you remember what was the cylinder? Yeah, the volume will be the same, yes. So this kind of objects we call the cylinder, right? Where the base is not a square anymore, or the rectangle. The base is a circle, right? So what kind of parameters will be given? So usually we're given the radius of the base, okay? The radius of the base. And we're given the age, okay? And finding the volume is the same idea. In order to find the volume, first of all, I need to find the area of the base and multiply this to the h, okay? What is the area of the base? This is pi r squared, right? This is the area of the base. And multiply this to the h, okay? Do you understand this? So for all of these cases, finding the volume was the same, right? I figure out the area of the base and multiply this to the h for all of the cases, right? Now, let's consider this situation. So let's say I've got some kind of solid object like this. Like this, for example. Okay? I would like to find its volume. I would like to know how much water it is possible to fill in to this object. Okay? So this is not the similar case as the previous ones, right? In the previous one, everything was like a kind of linear constant, and I could just find the area of the base and multiply this as h, right? This is slightly different, but the idea will be the same, okay? So can you tell me approximately, or can you tell me, is it possible to find a volume approximately? Approximately. How? For example, if I give you just a bottle of the water, so it looks like a kind of bottle, right? Can you tell me how to find the volume of the bottle? What is the idea? From engineering point of view, just tell me from engineering wise. Measuring the size of the bottle? But what if like a bottle is like this? Not like a straight. Yes? Okay. So what we can do is we can cut this to many parts. Okay? And by finding the volume of each of the parts, we can find the overall volume. Okay? The idea is like this. So I will choose some point, for example, here. Okay? And I will cut this. So this is kind of bottle, right? I will cut the bottle there. Okay? Let me cut it. So what kind of object you will have? Like this, right? And just like let me measure the distance delta x from this place, okay? And cut it here again. Okay? So let me cut it here. Okay? Do you understand this? So I'm taking this over there. So this will be this kind of object, right? Roughly. Solid one. Is it possible to find the volume of this object? This seems to me a cylinder, right? It is possible to find its volume more or less easily, right? The only thing which I need to know is the radius, right? Is this radius, right? If I know the radius, I can find its area. So the area will be equal to the pi r squared. Then I have to multiply the area to the delta x, right? So this will be delta x. It gives me the volume of this object, right? You understand this? So if I would like to find the volume of this bottle, what I decided to do is I just cut this into the really tiny slice here in the middle, okay? Or not in the middle, from the beginning until the end, okay? And I can find the volume of each of the slices, okay? By finding the area of one side, and by pretending that this is a cylinder, I can find its volume, right? By multiplying the area of the surface here, or the area of the base, to the delta x, I can find the volume of this piece, right? What if I will cut this to many pieces? Many pieces. How to find the volume? So I need to find each of the volumes, right? Then I need to sum them, right? So what do you think? Is it area depends on where I'm cutting? Does the area of the surface depends on where I'm cutting? Yes? So this area is different from this one, right? From the green one. It depends on where I'm cutting, right? It depends on x, right? So I need to find the area function of the area, which would depend on x, okay? What does it mean? It means that pretend that you need to write a program for this problem. So whenever you input the x, it should tell me the area of that slice, okay? For example, x changes from a to the b, for example, from 1 to the 10. If your program input asks me, okay, so enter the x, if I input the 2, it should make the cut at the 2, and it should tell me the area there, okay? If I input 5, it should cut this at the 5 and tell me the area, right? In all of these cases, the area of this base or the surface will depend on where I'm cutting, right? It depends on x, right? The idea would be to divide this area between A and B, again to the n pieces, right? With equidistant widths. So this will be delta x is equal to the b minus a divided to the n. I will split this to the n pieces, okay? And I will choose the sample points. Do you remember? The same thing we did previously. Then by finding the area for each of the sample point, and by multiplying this to the delta x, I can find each of the volume, right? The volume of one piece. If I sum all the volumes, I goes from 1 to the n, it gives me more or less the volume of the subject, right? But if I take the limit when n goes to the infinity, this will be exact, right? This will be more precise. So the summation of a of xi multiplied to the delta xi goes from 1 to the n. This will be, by the definition, actually, integration of the a of x dx from a to the b. Okay? Do you understand this? So in order to understand why this, I need to integrate this function, I need to come up with the engineering idea, right? So the idea was that if I had the object, in order to find the volume of this object, just cut this to many pieces, find the volumes of each of the pieces, and sum them, okay? And obviously, the volume of the pieces depends on where I'm cutting this, okay? So this should depend on x, okay? So the only problem, in most of the problems, we are looking for this kind of function, which gives us the area of the slice where we cut it, okay? So let's start with an example. So let's try to find the volume of the sphere. Yes? Exact area, exact area. When you take the limit, exact volume, sorry. So if you integrate this, it gives you the exact volume. Not approximate anymore. This will be theoretical exact volume, okay? So in a computer, you cannot do this, obviously. So for example, one of these software projects will be on this, where you will need to find a volume, okay? Very similar to the integration, okay? Where what you need to do is, you'll be given the solid, and you need to find a volume numerically by splitting this to the n pieces. For example, n is 10. Then you can calculate the exact volume using the integration. Then your program should tell me also what is the error between the numerical result and the analytical result, okay? Very similar to your software project on integration, okay? So let's do an example. So what I want approximately is this thing. So if I'm given a sphere, I would like to cut this to the many pieces, okay? So let's assume you're given an apple, okay? In order to find the volume of the apple, what you will do is you will cut this, for example, to the 5 pieces, 5 discs, 5 discs, okay? And by finding the volume of each of the discs and by summing them, you can roughly find the volume of the apple, okay? And obviously, you will see here from this result as well that if I take more pieces, the volume becomes very similar to the theoretical result, okay? Now, just using this idea, I would like to find the exact volume of the sphere, okay? So if I give you the sphere, what kind of parameter I need to give it to you? R, radius of the sphere, right? Depending on what is the radius, the sphere can be bigger or smaller, okay? So let's say we're given some sphere with the radius R. I would like to find its volume, which obviously depends on R, right? Let's find this. So the concept is important, right? So let's say we're given this kind of sphere, right? This is the sphere, okay? With the radius R. What I want is I would like to find its volume, right? Again, the idea is like this. So if the radius is R, and if I put the center of the sphere to the origin of the coordinate system, what will be this point here? This is R, right, on the x. This is also R, minus R, sorry, right? If the sphere has the radius R, and if I put the sphere, the center of the sphere, to the origin, to the center of the coordinate system, then this point will be R, this point will be minus R, right? Because the radius is R. Do you understand this? So the distance from the center of the sphere to any other point on its surface is equal to the R, yes? The point on the x-line. The point on the x-line is minus r. Okay, so now the idea is like this. I would like to split this into many pieces vertically, for example. Okay, so let's cut this here. So let's choose some point x, okay, and let's cut this here. So I will cut this here, okay. And could you tell me what is the area of this piece if I cut this exactly at some point x, okay? Because the only thing which I need to do is I need to integrate this function of the area from minus r to the r, okay? So I need to figure out what is this function, what is the area. So in order to find the area, so this is first of all the circle. You cannot see this, but you can imagine this, right? So this is the circle because this is a 3D. You cut this, there will be a circle, right? In order to find the area of the circle, I need to know the radius, right? Yes? So the distance from this point on the x-axis until this point, right? How to find this distance? So if I would like to find this distance from here to here, how to find this distance? By knowing the coordinates of this point, right? I need to know the coordinates of this point. Yes? So by subtracting their y components, right, y coordinates of those points, or by just taking the y component of this point, so x and y. So y coordinate of this point tells me the distance between the x-axis until this point, right? It tells me the radius of this circle, right? So if I know the x is given. You decided to cut this exactly at some point x is given. Is it possible to find the y? Yes, because I know the equation of the circle, right? Do you remember what was the equation of the circle? So x squared plus y squared is equal to the r squared, right? From here, I need to find the y, right? So y is equal to the plus minus square root of r squared minus x squared, right? So should I take it with the plus or minus? With the plus, right? So if you choose the x, so y coordinate of this point will be plus square root of r squared minus x squared. The y coordinate of this point on below will be minus r squared minus x squared. So the coordinate of this point here will be square root of r squared minus x squared. Okay? Like this. X coordinate and y coordinate. Y coordinate always tells me the height of the point. I mean, you know this, right? So x coordinate tells me on whether how much it is right or left with respect to the y-axis, right? Okay. So the radius of the circle is equal to square root of r squared minus x squared, right? Or basically the big R. Let's make it big R. Okay, big R is the radius of the sphere. The small r will be the radius of the circle where I cut it. Okay? What will be the area of the circle with the green? The area is equal to radius in the square multiplied to the pi. Right? So this will be r squared minus x squared multiplied to the pi. Right? So whenever you cut this, the area of the circle will be like this. For example, if you cut this at the point, so here this is big R from minus big R to the plus big R. So it changes from minus big R to the plus big R. Right? So for example, if you decide to cut this here, where x is equal to the big R, what will be the area? 0, right? Because there is no circle there. Exactly here also, if you put the x to be equal to the r, it gives you 0, right? If you decide to cut this here, where x is equal to the 0, what will be the area of that circle there? Pi r squared, right? So pi r squared, because x is equal to the 0, okay? You see, so this function gives you the area of the circle depending on where you're cutting this, okay? Now, in order to find the volume, what I need to do is I need to sum a of xi, right? You need to find the area of the circle and multiply this to the small delta x, right? Where delta x is this thing here. So this is the delta x, okay? So here, this is the delta x. So here, this is the delta x. Do you understand this? So we found out this area, right? we're multiplying this to the delta x in order to find the volume of one piece. Okay? Obviously, if you take the delta x smaller, then the volume will be more precise because you will have a lot of disks there. Right? Do you understand this idea? So now what we did is we figure out the function of the area, right? Depending on where you're cutting here, it gives you just the area here, right? Now, if you do this a lot of times, what you will need to do is you can find the volume of each of the slices by multiplying the area to the delta x, right? And if you sum everything, it gives you the volume. So in the limit, this is equal to the integration of the a of x dx. So dx means how the x changes, right? For this function a of x, how I can change the x? From which value to which value? From minus r to the r, right? That's it. Let's integrate this. So this is equal to the integration from minus r to the r of the r squared minus x squared multiplied to the pi dx, right? So what is the integration antiderivative of the r squared? Is r squared multiplied to the x, right? Because r squared is a constant. What is the antiderivative of the x squared? Is x cubed over 3, right? Then I have to put the values from minus r to the r, okay? So let's put the r. What you will have? You will have r squared multiplied to the r, right? Minus r cubed over 3. Yes? Minus pi multiplied to the, if you put the minus r, it will be r squared multiplied to the minus r, minus r in the cube over 3. Yes? Okay. If you open up everything, all the brackets, you will have pi multiplied to the r cube minus pi multiplied to the r cube over 3. Was this minus, it will be plus, right? It will be plus pi multiplied to the r cube. This minus, and this minus gives you minus, right? So this will be minus pi multiplied to the r cube over 3, right? So this is the same as this one, actually, right? So if you subtract 1 over 3 from the 1, what you will have? 2 over 3, right? So the first part is equal to the 2 over 3 pi r cube. The second part is the same, 2 over 3 pi r cube. If you sum them, you will get 4 over 3 pi r cube, okay? So the volume of the sphere with the radius big R is equal to the 4 over 3 pi r cube, which you knew before even, right, from the school. Do you remember this formula? The volume of the sphere is equal to the 4 over 3 pi r cube.